All right, Ken, take her away. Thanks.
All right, thank you. Go ahead and there it goes. See if we can get this shared. All right, thank you very much for having me here. I appreciate the opportunity. My name is Ken Miller. I'm a CTO for Keystone REN. I've been with Keystone REN, and we're the Pennsylvania statewide research and education network. Prior to that, I worked with ESNet for nearly 5 years with the science engagement team, giving talks like this on Science DMZs and research engagement, as well as working on the with the EPIC project as well. And then prior to that, I worked at Penn State for a number of years. Built the first Science DMZ there a while back, and then scaled it out to from the original 12 sites to over 30 different sites and telecom closets across 25 different campuses. So there's a lot of different opportunities here. Taking the same Science DMZ design pattern and then rolling it out depending on really the people network you mentioned earlier, um, and understanding the use cases and science drivers behind that. So. This kind of talk is into some of that directly from prior slides from ESNet and Epic, but then also goes into what we're doing across Pennsylvania with the REN at this point to look at how we can get smaller schools and different schools started with Science DMZs and paying attention to research transfers and other uh, details around that. So feel free to ask questions or we can questions at the end either way. So. Stepping into this, really the why science teams and why research networking matters. The biggest part about this is a lot of campus networks are built for utility and they're built for speeds and feeds, if you will, or they're built to really have a general purpose network so they can handle voice, video traffic, Wi-Fi, really anything like that. And a lot of times in the building, you have all these other ancillary campus services rolled in with where a lab is or an instruction classroom, library, things like that. And what goes into this directly is a lot of that converged equipment really isn't able to handle large transfers or you can't move an instrument into a data center. We've had conversations like that in the past. Data centers are built to handle what they handle, but you're really not going to put a cryo-EM or certain microscopes or um, gene sequencers in a data center. So you need to be able to move that to and from, the lab as to the data center or to the outside world. And that's what a lot of this is about. So networks are also more critical now, especially, after COVID, everyone kind of proved that the networks are quite necessary to be able to communicate, but also foster discovery and collaboration around this. A lot of traditional campuses, like I said, are not built to handle research or AI workloads. I know AI is, the big buzzword right now, but there's a lot of individual things around, not just the consumer grade AI, but also really the models around sending the data to AI systems that are out there. So a lot of this discovery is happening to, assist research, but a lot of the workloads around that too are be able to handle the data transfers to and from locations. Um, Firewalls, bottlenecks, and fragmented infrastructure can slow discovery as well as learning. And the solution, is a Science DMZ. It's a design pattern built to performance optimize a network enclave for research traffic. In addition, there's a spin on that too. We can actually look at it for low latency or remote control of instruments and things like that as well. And that's a different topic we can have. But there's a lot of different options with the Science DMZ design pattern to be able to scale out the use cases there. Combined speeds, consistency, security, and visibility. So this is where some of the people network comes into play as you work with faculty and to understand really what's really going on. This network is really about a conversation. It turns into infrastructure down the road, but really it's about a conversation up front to understand what the requirements are, the resources needed, and different things around that. But all the benefits except accelerates data discovery and collaboration, builds readiness for AI, large data transfers, and also access to and from national research projects or infrastructure, facilities, anything around there too, So it really depends on the workflow and understanding how people are utilizing the workflow across the network and then understand. So as we step into this, I'll kind of cover some things today. What is the Science DMZ? Why does it matter? Some of the key components around this, design examples, and what we're doing. One of the reasons I took this job was really looking at how we can cut down what we call the wizard gap, which is all these individual components from the people network that turn into design requirements that turn into, understanding the research workflow. I feel the regional networks are quite capable of taking some of this on and cutting down that wizard gap by deploying some of this. And that was one of the attractive pieces about taking this role, is looking to see what the regional networks can do to facilitate some of this happening at the campuses where we connect to, as well as how we connect to the national platforms like Internet 2, ESNet, NOAA, et cetera. So, and also steps and some funding around this too. What funding was out there in the past. We'll get into some of that too. But a lot of this is pretty easy to start and really doesn't have a heavy lift financially to get rolling on this. But one of the things I'll start with is, what is the biggest barrier to research data performance on your campus? And these are the kind of things that people, discuss here and there, but a lot of times, often as IT, we don't understand that, or as working in the HPC group, we don't really understand if there is a data transfer performance issue or anything around that. So these are just things we can kind of step into. So one thing I'd like to start off with in a lot of these slides is really understanding the data transfer estimates for 1 TB. That kind of is the standard at this point for a lot of this. So I want to raise your expectations a little to see where we should be, what you should be expecting to get on this. So if you're out in the field doing field research, Starlink and cellular point to points, wireless infrastructure, you might be able to transfer a terabyte in a week. Again, it depends on where they're at. There's a lot of variables around this too, but just rough numbers like this, looking at a week to transfer a terabyte. I think Scotty on here, he's probably got faster networks out there in the the field research side of things, but yeah, typically we're seeing transfers like this from different areas. Once you get back to campus and the Wi-Fi upload, it can be up to a day, depending on how well you're connected and things like that as well. Understanding how the data transfer rates are. Once you're wired into a campus, once you're plugged into Ethernet, you can take around 3 hours, if it's optimal, to transfer 1 TB. Then as you get faster, the times go down. But how many people really have a wired 10 gig in their office, or a wired 10 gig system related to this, or somewhere out in a lab somewhere? Some people do. A lot of campus networks are being upgraded and being able to support little faster speeds at the edge. But a lot of times it's really just the existing campus wiring in the facilities like this. So in a data center, it's not nearly as bad, because things are closer and you can control the infrastructure and the cabling a lot more. But for the most part, around 20 minutes. And then as you get faster, 25 gig and what was 45 gig, or sorry, 40 gig, 25 gigs now becoming the norm with some of this. You're seeing about a 7-minute transfer with optimal data transfer rates. And then with 100 gig Ethernet, we're testing a lot of this right now. We're getting great speeds on this, so you can actually transfer some of this. If you can hit the numbers and running with Globus and a lot of parallel transfers, you can get between 1 and 2 minutes on a terabyte at this point. So this happened a few years ago, but this was a test in the lab. So here was 1.3, almost 1.4 terabytes in less than 60 seconds. So again, this is a very controlled environment. These speeds are out there. This happened, I think, 2 years ago, 3 years ago. But these kind of speeds are coming to campuses. So as the technology increases, as different opportunities are out there, just examples of this are happening. So this is a data transfer scorecard. I like to start off with this to kind of level set where things are, again, talking about raising your expectations. Um, with a lot of times through, like mentioned earlier, the people network, we talk to different groups of people understanding a research workflow, but we all speak different data rate languages. A researcher might talk in terabytes per hour or something like that. Network engineer admin is talking gigabits per second. And a lot of times the system or storage admin is talking, megabytes per second. And so a lot of times we're, trying to understand each other, and we're all speaking different languages. So I developed a scorecard at ESNet to kind of look through those different pieces like this. And the petascale number above is the ability to transfer 1 PB. Um, so the idea around this too, transferring through here, we like to see a 10 gig capable DTN, at least at the minimum transferring 1 TB per hour or 2.2 gigs a second. Whether that's across campus, it should be able to do that. Whether that's to and from the outside world, these are just different things to kind of get into there. So looking at this directly is really understanding, where things need to be at this point. Again, this is just a general reference scorecard, but we kind of like to see where this is at going forward with some of this. We talked about this a lot with ESNet and Epic about having some of these data rates. But if you go out to the petascale column further out, you see a petabyte a week is really 13 gigs a second. So you're looking at less than 15% of a 100 gig connection to be able to transfer a petabyte in a week. And this is quite capable, but just throwing bandwidth at the problem doesn't necessarily fix it. And that's where the Science DMZ and some of the use cases come into play, as we're going to talk a little bit more. But the idea around this too is a petabyte a week is around, 15% of the network connection. But again, there's a lot of variables in between there that can kind of disrupt the flow of the traffic. So we'll get into some of that here in a second. So as we're stepping into this, many smaller colleges think Science DMZs are only for R1s and universities. But what's happening now, as a few years ago, where R1s were dealing with this, a lot of smaller campuses are running into the same thing now. And we're seeing this. So a lot of, the Science DMZ is happening at a variety of different levels across campuses, or even R1s are looking at separating out different Science DMZs for different types of traffic or different security requirements or things around that as well to make sure the transfers are happening. So again, the design pattern around this can quite flexible and deployed a number of ways, but we're seeing at least in the last few years, like an increase of the Science DMZ model looking at smaller campuses to benefit some of this because the amount of offload on campus firewalls and things like that can be greatly benefited. So, like I said, what we're looking to do is typically a campus network is really build the network, build the infrastructure for everyone, but it really doesn't call out kind of like the 80-20 rule, the 20% of the needs that are out there that are kind of specialized or that can kind of burden the campus network and things like that. So we want to make sure we're measuring how to improve scientific outcomes in some way. Things to consider, how does it work as expected? Just plugging in a wire. I had a graphic I was going to put in here of a sequencer I ran into on a campus once where the entire campus was over there and they needed one more port on the campus. So they went down to Best Buy and bought a little Netgear switch and plugged it into the sequencer, and the performance drastically dropped. There were only two network drops in that room at 1 gig each, but the fact that they plugged it into this little switch really bottlenecked everything. So all we did was move one wire over and plug it into the access layer switch. And it wasn't the most optimal thing, but just by paying attention and working through that and understanding, they really didn't want to pay a couple $1,000s to get new wires ran into that wet lab. But at the same time, buying a little device like that gave them connectivity, but it didn't guarantee performance. So it's working, yes, but is it working optimally? No. So as what we're looking at here is as we're engaging this, what will be satisfied at the end? How are researchers handling this? We can talk about surveys and whatnot, but really going back to that scorecard, we can kind of baseline to see where things are. And also, when are you ever done? So that's one of the things too, as we're looking at this. A lot of times we'll, increase the performance or we'll find a bottleneck or we'll open up some opportunities around collaboration. But a lot of this really comes down to understanding really what the needs are and also designing this with a little bit different state of mind as we're going into this. So this is from ESNet directly. It's looking at this. So the network is really not just the infrastructure anymore. We need to start thinking of this more like the network is part of the instrumentation or as part of the workflow directly. And that comes into play here. So yeah, connectivity is the first step, but usability must follow. And this is something that ESNet really pushes across this with the national labs and facilities like this. But we're seeing this designed around a lot of campuses over the last decade to make sure that we are paying attention to the usability of the network, but also, the speed and the security around that directly. So where do we go from here? Really, the who and the why are the most important questions. So that's what comes back to the people network mentioned earlier. Understanding, really where the researchers are, what kind of speeds they need, what kind of understanding, what kind of collaboration they need. And this will kind of design the technical solution. So a lot of these conversations will just, frankly, be as an IT, person, just go and just keep your mouth shut and listen because a lot of times you can kind of tease out the requirements you need to build the IT infrastructure around that. It might not be as it's built in the building currently, but there might be other opportunities with possibly moving just a few things around, whether it's configuration or just a different jumper, that you can actually build a quite optimal technical solution really with nothing more than just time to sitting down with the use case and understanding. The what and the how together really comes going into the other areas like this to have non-productive disruptions and slowing things down like this because we want to make sure we're building a solution that is implemented and so we can actually operate in an effective manner. So we have to address, like I said, item number one before we dive into item number two. So again, campus networks are really built around, a lot of different things, a lot of going on in campuses nowadays, and especially now that a lot of services are being moved off-site into cloud or software as a service, the network is becoming more and more critical in this aspect. So what happens is why research and any sort of science discovery or any sort of instrumentation on campuses, really the networks are designed to be access, but not really for performance. So there's a lot of times a bottleneck problem. Firewalls, NAT, security appliances can slow down traffic, but general purpose networks like this versus data intensive research can really, they're really not set up to do the same type of thing. Again, one is for access and one is for performance. And you just need to pay a little bit more attention when they're building out campuses like this where there might be instrumentation in that building and facility. Um, stateful firewalls over segmented networks are great for security, but multi-gigabyte data transfers from telescopes, genomic labs, and HPC clusters can be throttled quite a bit by some of this, just depending on the capacity and the type of data transfer and how frequently the data is transferred. Especially if certain systems are within a data center with administrative or academic systems in there. You think about virtual machines and other even Kubernetes clusters and things like that, but also the HPCs in the same data center on the same backbone. A lot of times, the transfers coming into there are quite throttled by the data center firewall at that point. So it's really not a traditional Science DMZ problem on the outside of the world, but it could be something going across campus that is also filtering and slowing down traffic between an instrument and the actual research storage location. So where we want to step away from this is looking at the network architecture. We now want to start looking at this as a data architecture, and we want to make sure we're understanding the components around this directly from, you go from the idea of what we're doing just to build infrastructure, but also what we're doing to enable workflows to be operated and more efficiently for collaboration and other things around that. So, understanding the data pipeline, and the data workflow around this can really help to define like really what's going on. And even a straw man diagram between these locations can understand really kind of break things down into the four things we're going to talk about. But for the most part, we want to make sure this is usable. We don't really want a walled garden. We don't really want to isolate everything out so it's not usable at all. We want to make sure there is an on-ramp to this to make sure you're easily onboarded, integrated. Related to this, when I was at Penn State, we called it the slow on-ramp, if you will. And once you get on there, you're kind of like moved over to the HOV lane, if you for those reasons, we wanted to make sure we had the engagement, the risk profile, everything else looked at from the researcher standpoint, as well as the funding agency and the compliance regulations around this. But once you're on there, we can kind of create the opportunity and build the security and build the performance around what needs to be. We want to make sure this is defensible. It's not the Wild West. This is not just giving people, open ports that are out there. The role I typically play is we put implicit denial rules on all the traffic to and from the DMZ, and then we only open up the ports and IPs that are filtered to be allowed through based on the engagement. So nothing's opened up until the engagement happens. That's one of the things we've actually built out for that model. We want to make sure it's scalable. So the cornfields and baseball diamonds. The idea around this too is to make sure that we have a design pattern we can reproduce, and we can scale it accordingly. So the science driver, the use case might be completely different, fundamental research in different areas of research, but the design on the back end to the infrastructure might be the exact same. They might, so just understanding these different pieces around this too, but also, this can turn into funding opportunities and also the source of pride for the university, making sure that, researchers, do talk to each other. Um, we used to go out to staff meetings and just talk about one group or hearing this or, another researcher in one department. Here's what we did for another department on a campus. And they're like, hey, we want what they had over there. And a lot of this, turns into a sociology piece where really just understanding, how we can actually enable the science to happen or the collaboration or, the instrument to be more efficient on campus. So this is again is a slide from ESNet, really kind of just describing this, putting the data as the center of all this because typically the other four circles around there too are different departments. And so the fact that they really don't talk to each other, but they all actually do something with the data in some sort of realm, really can kind of help foster that communication around that directly. And looking at this diagram can kind of get into there. And some people can say even the science in this picture can now be construed as AI and other discovery pieces around it as well. So this design pattern, making a data architecture, can really help scale out what campuses will need to take a look at. So. Some of the background information here, data movement, TCP background, really understanding, why things happen, why they transfer, why they get held up, really comes down to understanding the network protocols. And I'm just going to skip over some of this directly and just kind of high level, but really it's just understanding where the problems are. And we can sit down if you want to have a direct call or something, we can review this at another time. But it's really just understanding why the network performance is out there. Just because you're connected doesn't guarantee great performance. And so there are other things out there we can take a look at to make sure performance is happening. The way that the TCP works on this, it's really built to be resilient. And you really, if it does detect loss on the network, it'll just keep going. If it's congestion on the network, it's designed to back off but keep operating. And all this is great for communication and for, uptime. And no one really wants the spinny wheel or whatever on their screen. But the idea behind this too is it's made to be, keep going like this, but it doesn't, that model doesn't guarantee performance, and that's something that we want to work through on this. So no one really likes to either wait in line or wait for their app to load or things like this. So when you're running a transfer like this, taking 15 days to get between campuses, and we make one little adjustment change to link up the networks in the right way, fix the TCP problem on the network, and it dropped down to about 17 hours, I think. So you're looking at, weeks to days, or even less than a day at that point, just by making one software change when you start paying attention here. So again, the traffic was working fine, everything was working, it just was quite slow, and that's things like this can happen. So um, on this graphic, it's really understanding what happens, and we talk about that. The further away you are, the problem drops off drastically, and so we have this from ESNet as well, looking at the different areas like this. And typically, you're looking at the different areas where you get 10 milliseconds away and something like this. So I put this graphic on here just for the Pennsylvania people we talked to, but from Pittsburgh to Philadelphia across our backbone is around 9 milliseconds. So you can see just within our state, very quickly if there are network issues, and there better not be on our network, but if there are network issues, we want to make sure we can fix them right away, because even going across the state from border to border can really drastically reduce data transfer rates. So if you're looking at leaving your state or to and from your campus or anything like that, these different opportunities can really drastically reduce data transfer speeds when they're happening. So this is just something, again, a graphic I put over top of this just to kind of show within the state what's going on, let alone across the country or across around the world, depending on where your data is going to and from. And so this happens a lot when we talk about the community of networks. So between your campus network, how you connect to the outside world, you're going from one side to the other. You'll leave your campus network. You'll either go up through the commodity network or the regular internet, if you will, over to the regional network, to the backbone, to a regional, back to a campus network. So there's a lot of different things along the way that can really be a part of the problem on this. And when you're looking at this directly, there are a lot of areas where you might have congested campus links. There might be uplinks that are not configured properly. There might be long round trip times. We just mentioned that anything greater than 10 milliseconds, traffic drastically drops off. Um, so there's a lot of different things to come into play here when you're looking at this. So the easiest way to start with this is really understanding if it's your campus or not. And then there are other people who can kind of help decode the rest of it. But if it's somewhere on your campus, this is something where there are opportunities to kind of troubleshoot that and kind of work through that, depending on where how the workflow is transferring. But again, there can be a lot of problems depending on where we're going to and from. And we see this anytime we hop on the road. We go on trips somewhere, we load up maps or whatever, and we see where there are bottlenecks, where there's traffic, where there's anything like this. The research traffic is handled the same way. As you're going across the country, you'll see different areas around this where you might have a bottleneck, you might have misconfiguration, or you might be going down the wrong road, or the commodity network path versus Internet 2 or ESNet. All these things come into play as part of this. So. And again, this is where the small switch buffers, anything like this, anything around 10 milliseconds of performance, you can kind of see where performance really drops off if there are any things around this. So even if we test locally, we can get great performance on campus. The further away you go, you always want to kind of test across the country if you can, to see really what the bandwidth and the testing looks like. So. This is something too that happens a lot. This was actually presented, I think, at the Internet 2 meeting last year at the BGP workshop. But a lot of times, you'll leave your campus network, and it may look better going over your commodity provider. And this is something we do a lot on BGP tuning related to this. So it's better to kind of make sure we have the proper tuning in place, so that it goes over the national backbones. and through the regional networks versus just your campus or commodity network connection. But again, these are all the other things we can get into here. But a lot of this is really why we have these things set up. So we talked the data movement side of this and the TCP background really ties in together because once the performance is affected across this, the um, the data movement is greatly reduced, and that's where the Science DMZ comes into play to kind of build a model around this and a design pattern that can be scaled appropriately based on the data sets that's out there. Sorry, I'll get a drink here. So the four components of the Science DMZ are really a friction-free network path. This is really the idea, everything in one slide. We want to make sure we can transfer data to and from locations. We want to make sure the security policy and enforcement is built around science workflows and security is signed off on it. And we want to make sure that it's at or near the site perimeter. And so from there, we also have dedicated systems called data transfer nodes built to do this. And typically, this is dealing with Globus a lot of times on here, but there's a lot of other software too. But for the most part, these dedicated data transfer nodes are built to be able to move data efficiently related to this and tune properly as well. perfSONAR on here is really just a set of network testing tools that are out there so that you can do data transfers to and from locations, as well as doing single stream transfers, parallel transfers, looking at the path to and from a location to see if it is the same path to and from or different, to see if the path is disrupted along the way or has a misconfiguration. But really all this boils down to the the bottom bullet here is looking at the engagement with the end users and understanding really what the needs are and building all the other pieces around that on top of really what the engagement with the faculty or the researchers need. So again, IT may design something one way, but the user experience might be completely different. They want to make sure we can handle things like that as well. Because if we don't understand really what the requirements are, when we design it, it may not be appropriate, it may not be performant, it may not be anything really related to what they need at this point. So this graphic is something that usually cracks people up, but most college campuses have a path like this somewhere. So the areas around this too, as we're getting into the Science DMZ and getting started with this, really the design pattern which can be replicated. So we want to make sure this is something we can scale out and do appropriately, but depending on the use case or science drivers that are out there. This also creates an opportunity to engage faculty, IT, and security to have a conversation around the data and how it's being collected, transferred, archived, moved, collaborated on, computed, anything around this too. It's a great way to get everyone together on a campus to kind of see where the problem is, to understand, what kind of discovery is happening or what kind of science opportunity or what kind of instruments being deployed on a campus. All this really turns into the people network and the engagement around that to understand what the requirements are based on each group. Um, the idea around this too is building a dedicated network enclave for research traffic. So this can be done by science or by compliance levels or anything like this. But again, this design pattern is replicated, but building this network enclave around this really is just what we're trying to set up here. So typically we start out at the campus border router, but we've had some campuses look at bypassing the data center firewall in between an instrument and HPC because sometimes especially on a cryo-EM system, you're pulling terabytes of information off here, and that's being generated on campus and transferred across campus to the data center hosting the HPC, and the data center firewall is filling up log data just with the transfer that happened on campus. So we're seeing some campuses look at bypassing this, or there's some other things in firewalls called an ASIC bypass or an offload. To be able to make sure you're not inspecting all this traffic based on like a whitelist of the ability of certain instruments out there, or IP addresses, or certain protocols. So there's a lot of ways to kind of look through different things like that too. But this bypasses bottlenecks while maintaining security. We can look at the traditional versus Science DMZ architectures that are out there. So there's areas here where, as we look at diagramming out the network, you lay out one versus the other, and these different areas here can kind of look at that. But again, the key elements are the data transfer nodes, perfSONAR, a border, or even data center firewall, and then the routers around that. These different pieces around here, make sure when you're drawing the picture to understand the workflow, a lot of that will look like the network at some point. So as you diagram this out, it's a great way to look at that. So. Again, it can take on many forms. There could be a small installation for a project or two. There could be a new facility being built on a campus that is hosting a lot of instruments. And so there could be a dedicated segment of the network built a network enclave around that so that it can handle the research traffic going to and from those locations. There could be a dedicated router put in that building versus just an access layer switch to make sure data can be transferred efficiently, as well as there could be pre-processing systems in there. You're talking about edge computing and other things like that, so that quick analysis can be run as a sample's coming um, off an instrument or something. There could be some pre-processing done at that facility versus moving it to a data center or to a remote collaborator. So a lot of these things can happen on a campus. So it's really just mapping these things out and designing the infrastructure to support that. The science capability consume a majority of the infrastructure. So this happens quite a bit when you're doing a transfer areas around this that um, when you're doing a transfer like that too, the background traffic sometimes on a network device can actually slow traffic down. So having dedicated infrastructure can kind of help, build this out. Again, some of these use cases here are straightforward, some are less obvious. So it really depends on what we're trying to look at and what we're trying to design around and what kind of performance we're trying to piece here. But really, the idea around this is eliminating any sort of packet loss, packet friction, any sort of misconfiguration on the network switches and things like that. Because within a campus, things are pretty close. So you shouldn't have all those major issues and you can recover quite a bit faster. But again, the more the amount of data going through there or other pieces around this too on a campus, there can be many opportunities here. So a lot of times we look at this directly. This ad hoc DTN deployment is really just dropping a server somewhere else. Um, a lot of campuses, when you're getting started with the science, you don't really know where to begin. And we talk about this. The idea of perfSONAR at the border is a good start. So wherever your router is and connected to the outside world, um, even a legacy 10 gig server from an old system or something like that, you plug that out next to the border router, get perfSONAR running on it, and you find out the location. That kind of tells it if it's an us or a them problem, looking at a campus like that. And the second thing would be looking at a data transfer node. You put a persona next to the data transfer node or the instrument or HPC. Anything like that really kind of breaks the problem into multiple segments like this to determine where the problem is or is not. So. And again, this can be something delivered on a campus. The ad hoc deployment really is plugged into an access building switch, something like that, anywhere to that. So this is where a lot of these bottlenecks can happen on a campus network because you're just plugging it into whatever available network port you have, but you're not really engaging IT and you're not really engaging security around what's happening in the lab or on the instrument like that. You're just getting connectivity and off you go. So this goes back to the graphic earlier. You have product features out there, but user needs, and really understanding the idea around this and some of the CC Star grant efforts that are out there. The model around this is understanding where what the user needs are, because you can build a lot of infrastructure a lot of different ways, but if it's not usable, then really what's the point? You're kind of wasting time and wasting money, and you're kind of limiting you're kind of limiting the work of others if you're not doing it the most appropriate way. So when you look at these different pieces around this, understanding where the capabilities are and understanding where the requirements need to be addressed to make sure you're taking a look at this. So as we get into this next, just think about the science teams as separate express lane for trusted science traffic. One of the things we look into this too is as we're designing this and as we're building this out, as long as we have the appropriate people in the room designing this aspect and we're getting the right um, requirements built, both from the researcher, the compliance, as well as security, these different pieces around this. But we want to make sure this is also highly, reviewed, monitored, if you will, and also that it's not stopping at every little bottleneck across the campus. So this is a traditional Science DMZ design pattern where you have the transfer to and from the outside world, the most efficient way on a clean, friction-free path. This is again transfers to and from the outside. And then because you're close on a campus, it's really connected to your router. You bring it back in, you're less than 10 milliseconds. Even if there are issues within your campus or if your border firewall is not processing the traffic in the most efficient manner, you can recover that quickly because you're close, and that the greater than 10 millisecond rule really doesn't apply in this case because you're so close together. So you kind of get decent throughput in this copy. And Globus has a, a workflow already pre-built to do this called a double copy transfer. And so there's something else out there in Globus flows that takes a look at this and can handle that. But again, this is the overall view of and the design pattern that's out there. But again, this is just a design pattern. It doesn't have to be mapped out exactly this way because you can look at this directly. And as you start engagement around your campus, you can find different projects, different buildings, different areas where you can actually deploy systems like this. And a lot of times, if you have a campus and you can get dark fiber to certain locations, running a dedicated dark fiber out there and putting a better switch out at that location for that building just for the research transfer can backhaul that system and that data across certain locations pretty quickly. This is just an example of how to take the same pattern and replicating that based on, a dark fiber approach for individual security controls based on the actual science of the data being transferred there. This is another option around this, dark fiber to dedicated switches. Again, this kind of scales out a little bit further. So if you have a building with multiple tenants in it, or a building cluster, or some of this edge computing pre-processing systems like this, there are areas around this too where you can actually build and replicate multiple Science DMZ models out there, depending on how you want to scale that directly. So. This is a graphic that comes up quite a bit. There's a way that a lot of the instruments that you're looking at too, if it's a dedicated system with a control PC right here in the middle, that's actually leased by the actual instrument down below there. A lot of times you can't do real very much with that, but leveraging the capabilities of that control PC, if it can do a Samba mount or something like that, a Windows PC, that could be whatever. You can create a private connection back to a dedicated data transfer node, and this can actually bypass the bottleneck of this PC and some other storage around there so that you can actually get better transfer, better throughput to pull the data off the control PC directly to a data transfer node and get that back across campus or to the HPC center. So sometimes that control PC can get um, just kind of held up a little bit because of the architecture that's set up, or it's really not, you can't really modify or you can't really do any tuning on that since it's the least piece of equipment for the instrument. But leveraging what you can do with that, there are a couple other design patterns around there, what you can do with the instrument and the control PC around that. So as we step away from the design, we look at perfSONAR, and really we talked about that a little bit ago, but the idea around perfSONAR is really kind of like tuning your network, if you will. You take your vehicle in to get tuned up every once in a while. You're looking at tire pressures and cleaning your air filter and other things like that. This perfSONAR can kind of help with certain things like that that are looking at bottlenecks in your network, misconfigurations on your network, any sort of memory or buffer issues on your network. perfSONAR can kind of troubleshoot a lot of different things like that. So again, the easiest place to start there is plug it directly into your border router to start and just determine whether it's to and from your campus. Then from there, either put it directly on the Science DMZ, or if it's something within your campus, put it near the DTN or put it near the instrument at that point. Um, some people will look at perfSONAR at their border router and then directly in on their campus core that's right after the firewall to determine if there are already sort of anything going on with V4 or V6 through the firewall. I mean, perfSONAR, you can test quite a bit of different stuff with it. So it's quite flexible in what you can test with at that point. But having perfSONAR deployed at the border is by far the first and easiest start to take a look at. So. So from there, we want to make sure the network's clean. Make sure the wide area network is out there, the Science DMZ. We want to make sure that we are getting, on a single stream transfer, around 9 gigs on a 10 gig system like that. Anything more than that. Um, a lot of campuses now have 100 gig connections, but you're not really connecting everyone at 100 gig. You kind of want to map your testing platform so you're not, disrupting any other additional operational traffic. But typically, if your fastest customer on campus is connected at 25 gig, then set your transfers to test at 25 gig or something like that. You don't need to test the full 100 gig. This is not fast.com or a speed test you're running out there. You want to make sure that the actual transfers from your science traffic or whatever kind of speed you need can kind of get through those locations. So that's one of the things to take a look at when you're setting up persona in your testing paradigm that's out there. Um, I had a 100 gig network in the past, but the fastest campus or the fastest building was only connected at 10 gigs. So we ran our test at 9 gig just to make sure we could get between to and from the campus locations, to and from the data center, to and from the medical center, all at those speeds, because that was the fastest connection. We didn't have to run everything at 100 gig at that point. So. So we talk about software and data transfers. There's different pieces out there, and this slide's pretty old, but it kind of tells the story of really understanding the distance, how further away you are, but also the data transfers going through there. So the second row there is really a single stream that's out there transferring this at 6 gigs, and then the parallel transfer out there running 4 streams, you can get 8 gigs. And at this time, the system was disk limited. But again, the application out there can really help see where the bottleneck could be as well. Once we get the network clean, it really comes down to either the storage or the application at that point. And then so we're kind of just chasing around one performance piece after the other, and one bottleneck. Once you get that fixed, you're chasing the next, and that's where you kind of got to determine really what kind of speed you're looking at. And typically 80% of the 8 gigs here, you think is pretty efficient at that point. So these are the kind of different things you can look at. But the software side of this too, and software has greatly reduced some of the issues going forward. But this is just an older slide related to some of the transfers that are out there. So. This is a chart from ESNet looking at the data set size on the left and then the amount of time it takes to transfer that. You can kind of see here quickly the 1 minute, 5 minute, 20 minutes, 1 hour. We like to see over here 1 TB per hour in the 2.2 gig range. This is where we got that number to start with. And that turns into 1 TB per hour, 2.2 gigs, or around 280 megabytes per second to a storage or sysadmin. And so this is what we set up our initial baseline at. And then from there, we scaled it up to be, if we can get the idea of a 3 TB per hour on 20 minutes, it's around the 6 to 8 gig range. So that's where some of the opportunities come into play. As you connect at 25 gig, you can kind of see where, 22 gigs a second here is 10 terabytes in an hour. If you're running at that rate, that's fantastic. But again, these are all relative depending on the scale or the size of the data set, but also how clean the network is, or how tuned the storage or the systems are, or the applications. With all the different variables come into play here, we want to make sure this is all taken care of. So again, back to the data transfer scorecard. Again, looking at that same chart before, kind of take a look at this and see where some of your transfers are as we get into this. So. Once you have the network clean, this is an area where ESNet has DTNs that are out there, data transfer nodes, performance built, tuned to be able to handle data transfers. They offer those out to be able to transfer your data sets to and from. And so by doing this directly, you can click on this, run Globus, you can run these data sets, and especially the ones at the bottom there are 3 1 TB data sets, but they're all broken down. Each one will stress the system a different way. One will push more memory, one will push more disk IO. The top data set there at the bottom is 30,000 files, where the one on the bottom is 4 files, but they're each 1 TB. So you kind of get a variety of different tests out there, but this is just synthetic testing. If you have a real data set from a real researcher, please use that by all means, but this is just a benchmark tool that's out there. You can kind of take that and see where your speeds are. So to reiterate, data movement is hard to get right. There are many different components to it. We talked about a lot of the different areas around that, but software, server, storage, networks, but most importantly, the people. Understanding really what the data workflow looks like and things like this is relative to how the Science DMZ is built and designed. And getting started with this is really understand what the requirements are from the faculty or the researchers or anything else related to that. So testing may reveal what might not be ideal, but testing will also motivate to make it ideal. So finding a bottleneck, finding a performance degradation or a misconfiguration can kind of help you scale out as you start looking at Science DMZs. So having that perfSONAR at the border router to start with can kind of tell you, really what's going to and from. And also from there, there's a community around this too as we engage different people. There are opportunities out there to reach out to the community and see what bottlenecks are there, or reaching out to your REN to see what opportunities there are to kind of help clean some of this up and do some tuning. So the as we get back into this too, as we look at what we're doing across the state from the REN standpoint, cybersecurity is one of the things that comes up quite a bit, related to this. So again, this is just a high level view of what we're looking at, but the biggest thing is we deny all traffic by default. We only open up what we have identified through the science drivers and identified. And from there, we also turn up ACL accounting on this. So that creates a syslog event for every accepted or denied packet. And that's can be logged to campus security or a security system out there. From there, all accepted packets can be mirrored back to campus security if anything that is allowed through their pipe after the filtering is done by the ACLs. Also, sampling S-flow with the sampled packet headers or the NetFlow IPFix flow record being captured on the Science DMZ equipment can also provide an additional layer of visibility. Then also the routing optimization to make sure you're seeing traffic to and from those locations, as well as the flow data around that or back to the full packet capture. There's a lot of ways to tackle the cybersecurity on the Science DMZ. These are just a few ways that I've rolled it out in the past. So what we have running now. So what we're doing across the state right now is really we have a campus network that's out there related to these campuses, and we're building a Science DMZ to these campuses directly to help facilitate this, the speeds like this directly. And so as we're looking at this directly, we have the regional Science DMZ model takes a look at either hanging a dedicated data transfer node off the campus border router directly, the traditional Science DMZ area, or we can actually host this directly in one of our data centers for the campus, one hop away from their border router. In this regard, it really it limits the amount of change the campus has to do, but I'll step into that in a second. But by doing it this way, you have one router port to manage. We deny all ACLs we talked about a minute ago. It's a single server to manage, one system to tune, and one system to secure at this point. So this is the approach we're kind of taking with some of this directly. As we scale this out, looking at the campus model, this is the same diagram, just kind of turned on the side for what we show our customers. But the idea around this too is how we get started with the campus DMZ, Science DMZ, is looking at, the traditional model like this, where we have a dedicated router or a deep buffer switch that's out there connected to a data transfer node or a perfSONAR server. All this happens really right here based on the traditional model that's out there. As we scale forward, sometimes people call it a simple Science DMZ or something where they just plug the data transfer node or the perfSONAR server directly into the border router. That way you don't have to have that dedicated switch or a deep buffer switch. You can do all the tuning directly on an extra port right on the router itself. Typically, the routers have enough buffering in to be able to handle a transfer or a flow that's going through there. And again, it's really one area to turn off a port if you need to, if something is happening. But again, the capabilities around that too are that's one model at this point to take a look at. The other model is if the campus doesn't have an extra /24 or anything else related to the routing side of things, we can actually provide IP space and host this in either our Pittsburgh or Philadelphia data center. And the reason some RENs are looking at models like this too are it can help smaller schools or other campuses scale out and actually build a Science DMZ, even though it's right off the REN backbone versus the campus router backbone. And so as you're looking at this, to be able to deploy this, whether it's a DTN, perfSONAR, or even OSG systems or even NRP systems, this model can scale a little um, easier because it's actually done at the REN standpoint. So this is something we're looking at, and I know some other RENs are looking at this as well to kind of help campuses get started on Science DMZs as they're looking into this. And again, this model here is something else that's happening too on campus networks and DMZs that are out here. As you have an instrument related to this, sometimes campuses are bypassing the data center firewall or anything related to that. So you might have an opportunity here where the campus network is back to the data center firewall, but really you want the instrument data transfer to either be white labeled on the firewall or transferred directly to the HPC network. This is just another model that we've kind of built out for campuses to adopt and take a look at. So one of the things we're looking at here related to this too is looking at Globus flows going through here. Globus has documentation about copy and delete, double copy transfers, things like this to help automate some of these features around this. So as you're looking into this directly, there are areas and opportunities around this. And as of 2024, Globus has actually worked with perfSONAR and fixed a vhost configuration. So now you can actually run perfSONAR directly on a Globus server without affecting some of the issues. Now, the data transfers in the perfSONAR test are not in sync, so you can actually kind of limit where your traffic is going to and from. But these are just kind of pieces that are out there at this point. So um, let's see here. Oops. So the idea, the last piece on this really is understanding the Science DMZ. A lot of times we start out with just the top 10 reports on a campus network engineers or to and from your HPC cluster. You can start out with systems like that just to understand where your heavy hitters are on your campus and look at things like really the large transfers or the frequency of transfers, things like that. Um, The other opportunities, Epic and the NetSage data is out there as well. Take a look at. You can look at top flows by organization or top Globus tasks by organization. These are great ways to kind of click and see where when you select your campus, kind of what the data looks like and go through there. Again, once you find your use case, a remote instrument or anything like that, you can kind of do some testing on that, engage with the person directly, understand what's going on, but also identify the bottlenecks that are out there, and then document any sort of changes, improvements, and then from there you can kind of keep the process going and scale it out. Aside from that, building the DMZ, looking at a 10 gig perfSONAR server at your border, you can pick one up, relatively under $1,000 to start off with. You can actually use an older server if you need to, and just plug that right into your border router at that point. You can create a dedicated 10 gig segment off of that to start out as well. And then really, once you have the researcher out there, test the transfers to see what things are going to and from. Partnering with your REN can help you leapfrog some of this directly, especially if they are going after regional science DMZ opportunities. Some of the RENs can also host DTNs and provide templates and even help with your CC star proposal writing, um, at least in the past. We'll see where that's at. And then again, prior funding was out there to kind of help build some of these out with a campus design or a regional design. So I think that's it. I'm kind of close to time, so I apologize. So, um, any questions?
Thanks, Ken. We got time for like a question or two if someone has it.
All right, thanks.
I was going to ask what we could do to get started, but then you had that last slide, so you stole my
Yeah.
question already.
No worries. Yeah, it's really I hate to say it depends, but it always does, and it just really the science driver and the use case really comes out to start off with. But even the last piece here, start small. Pick a single use case. Look at your top 10 reports, whether it's to and from your cluster, to and from your campus, and start there. That's how I started at Penn State. We had one transfer we going between Penn State and Vanderbilt, even before the science team was even a thing. And we worked with, ESNet at the time and kind of found the bottleneck and the problem. And, one routing configuration change to increase it from weeks down to hours. So that's kind of how my whole process got started this back in 2011, I think. So, but yeah.
What are the strongest arguments that you think you see on really being able to successfully segment the science traffic from the enterprise traffic? We're currently in a big cybersecurity push, and they're
Mhm.
trying to really manage east-west traffic.
Yeah.
But we also have instruments. I've got a cryo EM, and
Mhm.
right now we can hit 10 gig without too much trouble. But if they move that onto their security posture, definitely there's worries that they won't know what to do with Globus.
Yeah, and that's one of the things that I've had to deal with that both on the security side as well as the financial side of things. I try to learn to speak their language. I try to work with the researchers and try to define the security plan or work with a security person who is willing to frankly listen and just understand and say, I want to build this in an appropriate way, but currently the bottleneck is going to be your security device, and it doesn't need to be there or that doesn't need to be the device itself. So, are there ways we can work through this and defining like an ISA plan or a security plan, or some people call them an ATO or an authority to operate? It's really about documenting the use cases around the instrument and why it's dedicated on there. And that's one of the dark fiber options I mentioned earlier is a great way to kind of work around that as well, to say we're going to transfer directly to the storage or even build a security enclave around that just for the cryo-EM secure campus data. There's a lot of different pieces around that too, but really, if you can get them to help speak their language in a way that they understand, even make it their idea, you can still make sure to say, I'd like to be able to at least get across campus, I want a 25 gig path all the way so that I can at least try to get 2 by 10 or, even a 25 gig transfer and just see if we can kind of model that around that. But yeah, the biggest thing around it is to try to build a security plan that they are okay with, or even loop them in and let them write the plan. You just say, well, here's where we're at, what we're going to do. Bringing up the performance aspect is one of the better things you can bring up ahead of time,
Mhm.
especially because the instrument's going to be here. And if you light this instrument up and they don't have the appropriate logging behind the fire camp data center firewall, Your cryo-EM transfer might fill the firewall logs quite quickly, to the
Mhm.
point where they might only have enough capacity to handle 15 days worth of firewall logs, for example. Ask me how I know. One transfer kicked off and it dropped the firewall logs down to about 2.5 hours. And they were mad about it. But again, because the transfer kicked off, the appropriate planning wasn't done to be able to handle large transfers, and it just filled the firewall logs on the data center. Um, so yeah, just bringing that up ahead of time and talking about the size of the data set, so how it might affect the firewall. You don't want to be the bad user at that point, but um, yeah, I just sit down and talk with them, and like I said, if you happy to reach out if you want to talk about.
Yeah. What sense do you have that your job has, I mean, what percentage of this work is non-technical, policy, writing documentation, all that stuff? I mean, I think a lot of us got into this field because we like the technical problems. And I think it would be helpful to have a sense for how much of the work for something like this is, not that.
Yeah, I mean, the original plan when I built this at Penn State years ago was there were probably 5 technology people in the room, probably 5 researchers, and about 8 security people. Because each one, there was one for vulnerability scanning, there was one for policy, there was one for architecture, there was one for the logging and the firewall, there was one. So I involved security from day one up front, and it kept getting to more and more just because I wanted to make sure that all the pieces were covered, so that we could actually handle this directly. But I'd say probably a third of the work is security and policy, around
Okay.
these type of things directly. Um, and the other third is probably just engagement with the researcher, understanding compliance, funding opportunities around that as well, that there might be other requirements around that. Some traffic must go through the firewall, and you can actually, in order to prevent some of the logging, there's that ASIC or the offloading I talked about earlier. Some data center firewalls can offload science traffic where it still goes through the firewall and it's still logged. It's just not logging every packet and inspecting every packet because it's coming from an on-campus known resource.
Yeah, we've had salespeople claim that they can do it, and then the promises of a salesperson do not
Oh
meet the
yeah,
reality.
yeah,
Yeah, no,
yeah. Now
Hey,
happy to
Ken,
reach. Yeah.
just quickly, we have a question in the chat. Do you recommend keeping the Globus node in the Science DMZ?
What was that again?
Do you recommend keeping the Globus node in the Science DMZ?
Yes, that's for sure where a lot of them are set up. Some of those big supercomputing clusters that are out there for the national systems, within ESNet, and the DOE, have a multiple range of Globus nodes out there, like Argonne especially, I believe. And they are PXE booted, and they're kind of like, just dumb appliances. And if something happens, they reformat them, bounce them again, and they get built on the fly. Globus has a way you can kind of create a multitude of DTNs to act like a single DTN. So you can have multiple nodes act like a single endpoint. But anyway, there's ways to do that around there. That way, we have some sites actually saying, well, we want a 100 gig DTN. I'm like, well, I'd rather buy 425s, because most transfers workflows are around 25 gig, and you can scale those out appropriately, and you can pause one so you can take it down, reboot it, patch it, whatever you need to do, and the other 3 are still running. So, but a lot of times the DTNs are sitting out there directly like that. Now again, depends on where the data transfer. If it's hosted through there, if it's connected to the backend storage, there's a lot of different ways to do that directly. But Globus has a lot of different ways to connect the data on the back end. So.
Sounds great. Well, Ken, thanks for the talk, and thanks everyone for the questions and attending, and we'll see you in the new year. Take care, all.
Thanks.